Okay, the purpose of our lesson today is going to be to refamiliarize ourselves with some of the terms from Algebra 1 that we may have forgotten over the last year or two. And we took a pre-quiz and looked at some of these topics. And I'd kind of like to believe that some of the people that struggled on the quiz the other day had more trouble with the quiz, not necessarily because we couldn't work the math in it, and I know that that may be a problem for some people, but mostly what I'm hoping is that maybe we didn't understand some of the vocabulary and the instructions. And let's face it, if you can't understand a word in the instructions, then a lot of times that can inhibit your ability to be able to actually solve the problem because you really can't understand the command that is being given to you. Well, looking at these review topics hopefully might help out. Now, of course, on the video, if you're watching at home and taking notes, then feel free to pause the video. I'm going to go through these definitions and explanations pretty fast, so just hit pause so you'll have enough time to get caught up. Let's begin. First off, your objective on your Cornell notes. Okay, you got a new line. Leave yourself a couple of spaces in between the last set of notes that you took. And now we are looking at a new objective. Today's objective is the student will remaster various parts or various Algebra 1 topics in order to be prepared for Algebra 2. Pause the video if you need to. I'm moving on. Okay. From the pre-test yesterday, one of the terms that you saw was the word solve. Now, hopefully this is one that we are completely familiar with. We've seen it 150 times. And basically, in order to solve, we are isolating the variable. Okay, solve means to isolate the variable. Another possible interpretation is to discover the value of the variable. And of course, solving happens only in equations or inequalities. So there needs to be some type of a judge in the equation, or a judge in an expression, in order for the expression to become an equation. So judges are equal signs, less than signs, greater than signs, less than or equal to, greater than or equal to. The next term we're looking at is simplify. Okay, well, hopefully this is one that we are familiar with as well. Simplify generally means to reduce as far as possible. And we reduce as far as possible by way of combining like terms. Now, combining like terms is one that gives people a lot of trouble, not because we don't understand what it is saying, but because we haven't, for whatever reason, haven't memorized the parameters for when you are allowed to combine terms or not. In short, we don't know what like terms are. Okay, well, combining like terms is just, in plain English here, adding or subtracting terms in order to condense an expression. And there are three conditions that must be met in order to combine. First of all, you must have the same variable or the same group of variables. For example, the only thing that you're going to combine with x's is other x's. The only thing you're going to combine with y's is other y's. The only thing you'd combine with gummy bears is other gummy bears, and so on. Once you've determined that you do have the same variables, okay, then those variables would need to have the same exponents. This usually hasn't been much of a problem through Algebra 1, but as you move into Algebra 2, it becomes more of a consideration because we're going to be seeing equations that not only have x to the first powers in them, but they may also have x to the second powers in them at the same time, or maybe even x cubed or x to the 1/2 power. We may see some fractional powers. So it's not just a matter of trying to add x's to other x's. It is a matter of adding x to the firsts to other x to the firsts, y squareds to other y squareds, z to the 1/2 to other z to the 1/2. And one thing dating all the way back to probably 5th grade or so is, once you determine that you do have the same variable with the same exponents and you're going to add them together, if fractional coefficients are involved, you got to have common denominators. Okay. Now, the first two of these conditions, having the same variable and making those variables have the same exponent, there's really nothing that you can do about that. If you do not have the same variables, do not have the same exponents, you're stuck. You will not be able to combine like terms. If you have a denominator problem, we can find common denominators so that the two terms can be combined. The distributive property. Okay, the distributive property is used when a value or a polynomial must multiply by another value or polynomial. Okay, and of course a polynomial is just a fancy word that means a number of terms. Okay, it can be as few as one term, like a monomial. It can be two terms, a binomial, three terms, a trinomial, and so on. But generally speaking, anytime you do multiplication, you are always applying the distributive property, even if it's only like a number times a number. That is a monomial times another monomial. One of the term in the monomial must multiply by the other term in the other monomial. Okay, and for those of you that may have had teachers that got really gung-ho on the FOIL method, they told you anytime you need to distribute, you do the FOIL method, and if you don't know what that's talking about, the FOIL, F stands for first, O stands for outer, I stands for inner, L stands for last, and that those are commands. You multiply the two first terms together, and then you multiply the two outer terms together, the two inner terms, the two last terms. I would like you to forget that method. It worked really good as long as all you are multiplying is binomials, but that's not all we're going to be multiplying. We're going to see some bigger polynomials. You may have some trinomials, some four-term polynomials, stuff like that. And if you only memorized FOIL and you try to do FOIL, you're going to find that you're going to miss out on a bunch of the terms. It's going to cause you to get the wrong answer. What I'd like for you to do instead is just to memorize this, that every term from one of the polynomials must multiply by every term from the other polynomial. Whatever polynomial is on the left, whatever polynomial is on the right, every term from the left must multiply by every term that's on the right before the distributive property will be finished. Slope, switching gears a little bit here. Of course, slope determines or explains the pitch and direction of a line. Once upon a time, back in the day, 6th or 7th grade, you first learned slope as rise over run. Rise over run is more of a description rather than an actual explanation or calculation, so you probably won't hear rise over run very much. One of the notations that you'll begin to see, not only in this class but also in physics and stuff like that, is the notation of delta. This little triangle here on this second notation is called delta. It's from the Greek alphabet, and delta's translation is change. So this little fraction that you're looking at next to rise over run, delta y over delta x. It means change in y over change in x. And that's just a more kind of mathematical way of explaining rise over run. Rise determines how much does the graph change on the y-axis as you move from one point to another. That is delta y, change in y. Okay, run means how much does the graph change on the x-axis as you move from one point to the next. That is delta x, the change in x. And one of the things you should be pretty familiar with over the last couple of years is the kind of the flavor of the month term that has come around is tests, tax, and EOC, and I suspect ACT and SAT as well, have begun to call the idea of slope. They've called it rate of change here lately. So anytime you see rate of change, that is a synonym for slope. Y-intercept, no great mystery here. The y-intercept is where a curve crosses the y-axis. And I put a curve rather than a line. Most people will say it's where a line crosses the y-axis. But you got to realize there are other things in graphs other than lines. We have parabolas, we have cubic equations, square root equations, absolute value equations, sinusoidal equations, and they all, or not all, but most of them, in a lot of cases, will make contact with the y-axis. So y-intercept is not a term that's just exclusive to lines. It applies to all kinds of curves. That's why I say where a curve crosses the y-axis. And it happens when the x value of an equation equals 0. A lot of people, when you ask them to find the y-intercept of something, they think they have to graph it. They think they have to use the calculator to calculate it. Absolutely not. If you have an equation that represents a particular graph, all you have to do is anywhere there's an x value in the equation, turn that x into a 0. See what happens to the rest of the equation. You're going to end up with a number, and that number will be your y-intercept. Slope-intercept form, that was another thing that popped up on the quiz yesterday. Hopefully everybody knows that slope-intercept form is representing a line, and the format is y equals mx plus b, where m represents the slope of the line, and b represents its y-axis intercept. All right, some extra terms. Okay, a function. A function is a graphable situation where no x value has more than one y value to accompany it. Okay, that's the actual technical explanation of it. You may have had a teacher at some point that told you in order to determine if you have a function, you do the vertical line test, which means that in your graph, you just start drawing basically an unlimited number of vertical lines, and no vertical line that you can place over your graph is allowed to hit that graph more than once. Because if it hits the graph more than once, that means that at one place on the x-axis, there are two y values going along with that x value, and that's a big no-no when it comes down to functions. Domain is a term we should be familiar with over the years. Domain is all of the possible x values for a function. Now, depending on the function, sometimes the x you may have an entire domain all the way from negative infinity to positive infinity, depending on what the graph is doing. Or maybe the domain will come from negative infinity but stop at some point. Or maybe it begins at some point, goes off to positive infinity. It's possible that your graph might just be a collection of points. So your domain just might be several individual numbers that are on the x-axis. It just depends on the graph. And of course, range. If domain is all the possible x values for a function, then range is all the possible y values for a function. And the same basic idea applies to that. Now, if you're one of the people that understands domain and range and understands that it is x's and y's, but maybe you get them confused, you're not too good at remembering, is domain the one that's talking about the x's, or is it the one that's talking about the y's? And the same thing with range. The little simple way that I try to give it to like Algebra 1 students so they can remember it is that think about it alphabetically. Alphabetically, domain comes before range, D comes before R. And then if you think about the axes that you're working on, you've got an x-axis, you've got a y-axis. Alphabetically, x comes before y. So you've got D before R alphabetically, x before y alphabetically. So the D and the x go together, the R and the y goes together. Domain is x, range is y. Maybe that'll help you keep it straight. Discrete. This is something that, I mean, if you had a pretty good Algebra 1 teacher, you may have a good idea about this. If you didn't have a good Algebra 1 teacher, maybe not. The idea of a discrete function is something we're going to be dealing with a little bit. When a function assumes only certain values in an area on the number line, this means like maybe there's points in our graph, just plots, and they're not connected. So we have pieces of the graph that exist, but in between these pieces, there may not be anything connecting them. So there are maybe like a point at 2 on the number line and a point at 3 on the number line, but nothing at 2.5. Well, 2.5 is a real number, and it's sitting there on the number line, but for whatever reason, our graph isn't reflecting that particular number. That is a discrete function. On the flip side of that, we have continuous functions. Continuous functions will not skip over values in an area. Okay, when a function assumes all values in an area on the number line. Time is an example. I could say, hey, I've got a graph here. It represents the time elapsed between 2 o'clock and 3 o'clock. Well, 2 and 3 are definitely part of the graph, but did time exist all the way between 2 o'clock and 3 o'clock? Yes, it did. That is a continuous function because all of the fractions in between 2 and 3, all of the decimal points between 2 and 3 would be represented in some fashion based upon that graph. Okay, system of equations. All right, system of equations is something we're going to deal a whole lot more with in Algebra 2. In Algebra 1, you mostly deal with one equation at a time. You did get into some systems toward the end, but a system of equations is when two or more equations are required to describe the variables. And basically the need for a system of equations depends upon how many variables you have in the problem. Typically, you need at least as many equations as you have variables. So if you have an x and a y in a single problem, you've got two variables. That's going to take two equations to describe it. If you have an x and a y and a z, that's three variables. It's going to take at least three equations to describe that. The term equation, simple enough, we've heard it forever. When two expressions are set equal to each other. So whatever is on the left side of the problem, whatever is on the right side of the problem, they are set equal. The equal sign acts like a balance scale. Those two sides always balance. And that's our job, our chore with Algebra 2, or with any algebra, is to make sure that while we manipulate the expressions on the either side of the equal sign, we don't do anything that upsets the equal sign and makes it unbalanced. Inequality, we're going to deal with inequalities more this year than you have in the past. And simply speaking, that is when one expression is potentially larger than the other. Why do I put potentially larger than the other? Really quite simple. It's potentially larger because we have some judges that show the possibility of something being larger or smaller, but also being equal to, like less than or equal to signs, greater than or equal to signs. One side isn't necessarily bigger than the other, but it is a possibility. Okay, parent functions, something we should have heard over the years. And basically speaking, a parent function is the most basic, unaltered form of a function. In plain English, that means that the graph, whatever it is, whether it's a line or a parabola or an absolute value, whatever it is, it hasn't been disturbed in any way. It hasn't been vertically shifted. It hasn't been moved up or down. Hasn't been phase shifted, moved sideways. It hasn't been made steeper or shallower. It's not hadn't been more vertical. It's not more horizontal. It hasn't been turned upside down. Anything like that. So those equations are typically, when it comes to linear, y equals x. The most basic, unaltered form of a line is y equals x. Y equals x squared. That is the most basic, unaltered form of a parabola, and so on. Linear function, obviously. Everybody knows linear function graphs a line, but what actually makes it a line is when you look at the equation itself, both variables are first dimensional. You have x to the first power, you have y to the first power. That's what makes a line actually be a line. Quadratic function. Okay, quadratic has bends in it. The only way that you can bend a graph is to start changing the exponents of the equation that belong to that graph. And to be quadratic, one variable is going to be first dimensional and the other one is going to be second dimensional. Okay, for most of us, when we've seen parabolas in the past, that has typically been y equals x squared. The y has been first dimensional, the x has been second dimensional. That caused the parabola to either open upward or open downward. Okay, we haven't really gotten to it yet, but you're also going to see that parabolas can also go sideways, and that happens with x equals y squared. Okay, so when the y is the second dimensional variable, it'll open the parabola sideways. We don't deal with those much because they aren't functions. And of course, a quadratic function graphs a parabola. The next thing we kind of need to know is the 5 steps to solving equations. It's great to know what an equation is and how it's balanced and it's got expressions on each side, but you better know what to do in order to solve it. So this is a review of kind of the end of pre-algebra and definitely Algebra 1. So if you need it, here it is. The 5 steps to solving equations. Mine may be a little different ones that you've seen in the past, but bear with me, I'll tell you what they mean. My step 1 is parentheses. If parentheses exist in the problem, we need to deal with them. Step 2, combine like terms. Okay, combine like terms. That is step 2. Step 3 is that the variable goes one way, meaning if we have variables on two sides of the equation, if they're on both sides of the equation, we don't want them on both sides, we just want them on one side, so we're going to send the variables one way or the other. Step 4, everything else goes the other way. In step 3, whichever direction your variables went or already existed, everything else is going to go the opposite direction. So if you decided that the variables are on the left, then that's fine. Everything else that's not a variable is going right. And step 5 is what I call 1 and 1. Okay, 1 and 1 is referring to the condition of the variable. The first one refers to the variable's coefficient. We want the coefficient of the variable to be a 1. And the second one of the 1 and 1 is referring to the variable's exponent. Whatever our variable is, we want it to be in the first dimension. So 1 and 1 means a positive 1 coefficient for the variable, and then a positive 1 exponent for the variable. Now, I cooked up a goofy little way to try to remember this, and that's partly the reason why my wording and my 5 steps may be different than what you have heard in the past. And my little acronym, my little saying is parents' complaints vary for everyone. Okay, and if you look at the first several groups of letters for each of the words in my acronym, parents' complaints vary for everyone, you'll see a direct connection between the first several letters and the step that you're supposed to be performing. For example, parents, PAR, the PAR hopefully will trigger in your mind that the first step is parentheses. Okay, on complaints, COM, the COM hopefully will trigger in your mind that is combine, combining like terms. The VAR for variables going one direction, the every for everything else going the other way, and the one hopefully will trigger the 1 and 1. So parents' complaints vary for everyone is parentheses, combine, variable, every, one. Parentheses, combine like terms, variables go one way, everything else goes the other, and you're 1 and 1. Okay. Now, in order to do that, I mean, once you've got it memorized, and that's kind of the important part, you got to be able to remember the 5 steps before you're going to be able to do anything with them. But of course, once you've got them memorized, now you've got to know, what do I do with them? Well, if you run into parentheses, if you have a parents problem, parentheses, that's the distributive property. If parentheses exist, if you'll perform the distributive property, that should allow you to remove the parentheses from the problem, and you'll be free to move on to the second step. Step 2, complaints. Complaints is for combining like terms. Well, you better know when terms are like, and we already talked about it. You got to have the same variable, you got to have the same exponents with that variable, and if there's denominators, the denominators need to be common. Now 3, 4, and 5 I grouped here together. The variable going one way, everything else going the other way, and the 1 and 1. The math is all the same, or the same concept for all 3 of these. And basically what we're looking at here is these 3 steps all involve things leaving one side of the equation and appearing on the other side. Step 1 and step 2, if it was on the left, it's happening on the left. If it was on the right, it's happening on the right. 3, 4, and 5 are going to involve things going from left to right or from right to left. Okay, so we're sending things from one side of the equation to the other, and in order to do that, you must do the opposite of whatever the problem says to do. So if you want to move something that's like plus 6, you've got to ask yourself, well, what's the opposite of plus 6? Well, the opposite of addition is subtraction, so I'd have to subtract 6. If I've got something that's being multiplied by negative 4, then you got to ask yourself, what's the opposite of negative 4? That would be, or what's the opposite of multiplying? The opposite of that would be dividing by negative 4. And of course, the one thing that you've absolutely got to pay attention to at all times is to keep the equation balanced by performing identical operations to both sides of the equal sign. So if you want to add 6 to one side of the equation, you better add 6 to the other side. Otherwise, you have unbalanced the equation and it's no longer equal. You will get an incorrect answer. That will be that. If you want to divide by negative 4 on one side, that's fine. You better divide by negative 4 on the other side. Okay. Here we have some example problems, and we're going to walk through our parents' complaints vary for everyone. Okay, so question number 1 here, parents. What does parents refer to? Parents refers to parentheses. There are no parentheses, so we can skip past it. Step 2, complaints. Okay, complaints refers to combining like terms. So we look at the left side of the equal sign and decide, are there any terms that can be combined? Well, it's only a monomial. There's only one term out there. You're not going to get to combine any of that. So nothing to do there. You look at the right side. Again, it's only a monomial. Nothing to combine. So can't do step 2. Parents' complaints vary. The vary refers to the variables. Get all your variables on one side. We can see that they're all already over on the left side. Okay. Parents' complaints vary for every. That means everything else that's not a variable goes to the other side. Well, we don't have anything attached to the variable, so we don't have to worry about that either. We've gone through the first 4 steps and nothing to look at. The only thing for us to consider here is on the 1 and 1, we are supposed to have a positive 1 coefficient and a positive 1 exponent. We don't have a positive 1 coefficient. We don't have 1x. We have a fifth of an x. Well, we don't want the fifth of the x, we want the entire x. So what is the opposite of x being divided by 5? The opposite of x being divided by 5 would be multiplying by 5. But whatever you do to one side of the equal sign, you must also do to the other in order to keep it balanced. We have 5 divided by 5. That'll take that away. X equals 3 times 5 is 15. You can plug that back into the original problem to see if you got it and see if it works out. Okay. Next, again, parents, parentheses. Okay, no parentheses. Complaints, combine like terms. Well, we have a binomial on the right side this time, but as we look at those two terms, we see that they are not like. We have a y and we have a 4. Y is a variable, 4 is a constant. Variables and constants are not going to want to combine. Vary. Okay, we need to get the variables all on one side of the equal sign. They're all already on the left, so nothing to do there. Everything else must go to the other side. Well, our variable is not isolated. It is not alone. We have a plus 4 attached to it. We don't need the plus 4 attached to our variable, so we're going to move it. What's the opposite of something added by 4? Subtract by 4. And whatever we do to one side, we do to the other to keep the equal sign happy. The y is still there. 4 take away 4 is 0. Takes care of that. The equal sign will always be there, so there it is. We had 56 of something. Now we took 4 of them away. That leaves us with 52. We can always plug back in and check, make sure it works. All right, question 5 over there, very much the same as question 3. Okay, no parentheses, no like terms to combine. No variables are already in one spot. We get all the way to step 4. The variable is not isolated. We have a minus 3 attached to it, so we're going to move it. What's the opposite of minus 3? Add 3. Whatever you do to one side, you must do to the other. That leaves you 7y on the left. The equal sign is there, and 25 plus 3 more is 28. This time we get to step 5, and we find we do have a step 5, our 1 and 1. The first one is looking for a positive 1 coefficient for y. We don't have 1y, we have 7 of them. We don't want 7, so we got to move the 7, leave the y. What is currently happening in between the 7 and the y? They are being multiplied. What's the opposite of multiply? Divide. Divide both sides by 7. Y equals 28 divided by 7 is 4. Plug it back in, see if you got it right. The next part of that pre-quiz that gave us trouble was give the slope and y-intercept for each function. Well, hopefully now that we've refreshed the idea of slope-intercept form, we know that slope-intercept form is y equals mx plus b. Once we have our equation in that format, we know that m represents the slope value and b represents the y-intercept. Very nice. This problem is already in slope-intercept form, so all we have to do is read the values straight out of it. M is the number in front of x. It's the coefficient of x in slope-intercept form. What's the coefficient of x? It is 3. B, when you're in slope-intercept form, is represented by the constant. What's the constant in there? 7. The next part of the quiz that gave us a little trouble was to actually write the equation in slope-intercept form. Currently, this is what we call standard form, where you have all of the variables on one side of the equal sign and all of the constants on the other side. So what we want to do is we want to be able to convert this guy from looking like it is ultimately into looking like y equals mx plus b. So all we're going to do is just start shifting things around to make this look like it's supposed to look. Okay, it's kind of like solving your equations. Right now, we have y's on the left side. That's what we're trying to isolate for. And it's got some x's attached to it. Those x's do not need to be there. So we're going to move the x's to the other side. So how do you move these 3 x's? You're going to subtract them. Now, how did we know that they were being added Okay, because subtraction is the opposite of addition. We must know that they're addition. Well, anytime you're looking at the lead term of an expression, which is the leftmost term, whatever its sign is, that is what is happening to it. If it's a positive, then it's being added. If it's a negative, then it's being subtracted. So since it's a positive 3x, that means it's being added. So we're going to subtract 3x from both sides. That will leave you 2y's equal to. Now, what about these two? Are they like terms or no? Well, let's have a look. Are they the same variable or the same group of variables? Absolutely not. 12 is a constant. X is a variable. They will not combine. The negative 3x's are going to be there, and the 12 constants are going to be there. The last thing would be all the way down to your 1 and 1. We have two y's, but we don't want two y's. We just want one of them. So the entire equation would need to be divided by 2. When you do that, you would be left with just one y, which is what we want. The slope, negative 3, would be divided by 2. That's negative 1.5, but typically slope is left as a fraction, even if it's improper, so we'll leave it as a fraction, negative 3/2 x. And then you have 12 divided by 2. That's 6. So your slope-intercept version of 3x plus 2y equals 12 is y equals negative 3/2 x plus 6. Simplify by combining like terms. As we said earlier, simplify just simply means to condense it down as far as it can. Now, condensing it down, as it says, is by combining like terms. We want to add or subtract as much as possible in order to condense it. My particular habit I've gotten into is to underline when I am combining like terms, because unfortunately one of our mistakes is we lose terms when we're trying to combine like terms for some reason. So I underline them to make sure that everything actually gets taken care of. So right off the bat, I have 8 x's. What do x's want to combine with? What are their like terms? Other x's. I've got x to the first, so I'm looking for more x to the first. Are there any? Yes, there are, right there. Notice that I underline not only the two x's, but also the sign that is in front of them. Remember that in mathematics, a sign belongs to the value that follows it. 8 x's, take away 2 x's. Are there any other x's? No, there aren't. That will leave us with 6 x's. Then I just scooch over to the next term that is not underlined yet, and I find that I have 5 constants. What will 5 constants want to combine with? They'll want to combine with other constants, so let's look for more. Are there any more? Yes, there are. Here they are. There are 12 of them. And again, I underline the sign that comes in front of them because that sign belongs to the value that follows it. So I have positive 5 constants, then I have negative 12 constants. When you combine those, that is negative 7 of them. There, that is combined. It's simplified by combining like terms. The next part of the pretest was to simplify by using the distributive property where needed and then combining like terms. Well, folks, so I told you about the distributive property is when you decide that any values need to be multiplied by any other values, you simply remember every term from one polynomial needs to multiply by every term times the other polynomial. So this little x that's right there, I am going to make that x multiply by everything I can find in the other polynomial. So x is going to multiply by x, that is x squared. X is going to multiply by 2, that is positive 2x. Now that x has multiplied by everything over there, now I scooch over to the next value, which is negative 5, and that negative 5 needs to multiply by everything on the right. So that includes getting the x and the positive 2. Negative 5 times x is negative 5x, and negative 5 times positive 2 is negative 10. The distribution is done, but you always check for like terms to see if it can be simplified. Okay, well, let's have a look. I've got some x squareds. What do x squareds want to combine with? Other x squareds. There are not any, so they are going to be part of the next step. I scooch over. Next, I have some x to the firsts. What do x to the first want to combine with? Other x to the firsts. Are there any? There sure are, right there. There are 2 of them, and then there are negative 5 of them. That is negative 3 of them, so they will appear in the next step. Then the last thing I see is a constant. There are negative 10 of them. Obviously, I've underlined everything. There are no other constants to be found. So there are your negative 10 constants, and there's your answer. Okay, the next one, there is distributive property, but be very careful on this one. Okay, a lot of people will want to take the entire 4x minus 3 and multiply it by the entire 2x plus 6. The problem is the entire 4x minus 3 is not multiplying by the 2x plus 6. What is actually multiplying by the 2x plus 6? Just the value in front, and it's just the value in front because there's no parentheses around this 4x minus 3. It's just the negative 3 out there. So negative 3 is going to distribute into the parentheses. So 4x is just going to sit and wait for a minute. Negative 3 times 2x is negative 6x, and negative 3 times 6 is negative 18. The distribution is done. We're going to have a look and see if there's any like terms to combine. I have some x to the firsts, so I'm going to look for more x to the first, and I find some right there. 4 of them, take away 6 of them, that is negative 2. And I have negative 18 constants. Obviously, there are no other constants to combine with, so there is our answer. Your assignment at this point is we just covered half of the questions, or approximately half of the questions from the pre-quiz. After getting the notes that you got, the refresher on the different terms and operations and steps and stuff like that, and seeing these other problems worked out, you should at this point in time be able to go back and work the remaining questions on the pre-quiz. So that's going to become your assignment. Everything that we did not just work out together, you need to work out on a separate sheet of paper, because your pre-quiz probably already has some scribblings and stuff on it. On a separate sheet of paper, work out your pre-quiz problems that were not just covered in the lesson, and those will be due the next time we meet.